I'll see how long I can go. Good afternoon, all of you. And today I'll be trying to speak on synchronization and localization of IoT or sensor network devices, where particularly what happens is when we put a large number of nodes and all, addressing them and finding them exactly in which place and all will be very difficult. Because most of the times what we do is if the area where we are trying to go is unreachable, we have to use some mechanism like dropping them someplace and then trying to monitor and all. So we don't know exactly which location the sensor is or the coordinates of the sensor network, we are unaware of it. In such cases, we want the localization, and at the same time when you are getting data from multiple inputs, we want a synchronized data. So these will be the main topics which I'll be covering right now, and we'll try to see some application where exactly this timing information and the location information is critical. Like for example, when we try to see the vehicle-to-vehicle communication, the vehicle timing should be same. The one should not say 10:5 or that should not say 10, because this will send a signal and it assumes that the vehicle is far behind it and then try to communicate and all, even though they are parallel to each other. So in such condition, in a distributed nature, when you have a distributed vehicles around in an area, and if the communication is not synchronized, then the vehicles will lose the track of the information and they will collide with each other. So the time has to be very specifically synchronized among all the devices. That is one condition. And second one is even in the robotic critical operations and all, they have to be synchronized properly. Otherwise, they will lose the commands and they might do whatever they want. So there are some networks which are time sensitive networks. We want time has to be precisely be synchronized among the nodes. So this is a scenario where you can see that we have the access points on the road or the base stations on the road, and the vehicles are communicating among themselves extensively for all the communication purposes, and they are trying to interact with each other so that they can move in a coordinated fashion. Otherwise, they will be losing the track of time and they might be moving faster and slower and they might hit each other on the road. Right? So if you try to see, we have a particular equation, D is equal to, you have D is equal to T into C naught, so you can easily find out. It is not that difficult to find out exactly what is the delay between two vehicles and so on, distance and delays you can easily find out. So the timing information also helps us to exactly locate where the vehicle is. Okay, it's not that the location will help timing. Timing will also help exactly where the vehicle is, or where the mobile phone is, or where the IoT device is. And if it is the timing is not synchronized, you will be losing something like around 10 to 100 meters distance. Exactly, you will not be able to precisely find out the location. So we have different methods of doing that. We'll come to it in the localization. We'll treat the timing information first, and then we go to that localization. So it's not only the location of the vehicle and all, even when we try to look into the MAC layer where there are a number of devices want to communicate among themselves, we want the media access to be also synchronized. Like the vehicle has to precisely come in the red slot and send the information or get the information. Yellow vehicle has to come exactly in the yellow slot and they have to communicate. The green has to come into the green slot and communicate. It is not that red can come in the yellow and communicate, or yellow can go into that. And even one bit jump over here spoils both the communications. So that is very critical over here. The timing is very critical, and they have to exactly come in the slot. They have to finish the communication, and next slot, the next vehicle will come, and so on. So this is one important thing, and it is in milliseconds. And assuming that it is 97.2K. If it is more than that, this will go into microseconds also. So we don't have these luxuries like we can do whatever we want at whatever time and all. We have to precisely use our timing. We have to finish off our communication and move out of it. so that the next vehicle will come here, and so on. This is TDMA, so you have to move according to your slots given to you. So not only that, even the data fusion also we need it. Like when you're collecting the data from different sensors and we are trying to send it to the server, they have to be synchronized very precisely. So this node will wait for these two data to come in, and its wait time is 0.6, and if this sends you after 0.5, the data is lost. So when we are trying to mix the data also, the timing is critically important. When we are communicating, critically important. Finding the location, it is also important. So for example, we are trying to monitor the vehicle movement, the yellow vehicle movement on the road. And at 10:30, you have pointed out this, and 10:36, it is showing as 10:30.34, which means that in the scale, if you try to see, this is moving back of it. Right? In the time scale, if you try to see, this is supposed to be here, but it is here because there is a small delay gap over here between the timings of the two vehicles. It is assumed that this vehicle is moving backwards, not forward. Right? So based on the timing, if we try to analyze, this vehicle is moving back, not front. So the timing plays so critical in case of distributed networks, and we have to give utmost care because the timing interval what we are trying to look at is microseconds and less than that. So now to get this information of the time, mostly we say that GPS is there and all, and or we have a popular computer network strategy where if you put on your laptop, automatically the timing information comes from server, it gets updated. Right? Even if your mobile phone, if you try to see, it talks to the base station and get updated. You need not have to. That is what we call it as NTP, Network Time Protocol. They automatically move up and down, and then they try to precisely find out the timing using internet. And this is from the satellite, GPS satellite. And these two, if you try to see, they are power hungry. They are not that small energy devices and all. You have to get the information from the satellite, and it consumes a lot of energy, and your devices don't have that much energy to do that. So you can test it, like keep the GPS on your mobile, and you can see that the battery drains faster. Right? So this is a very power hungry methodology, and does not suits for IoT. And it's not only that, it does not penetrate to the walls and so on. We have to move to some other strategies rather than GPS. Okay? So if your IoT devices are in your cellular network, the GPS doesn't function. Like cellars and all, it's not cellular network, cellars and all. Right? So this is another big problem over there, and even nowadays, the indoor GPS we are not trying to use, we are using Wi-Fi timing extraction and all. Right? So these are some of the problems with the GPS arrangement, and we assume that it is not suitable for IoT devices which are placed externally outside and in an area where the GPS signal cannot reach that place. And even if it reaches also, we are not in a position to keep GPS on all IoT nodes because they drain the battery faster. And coming to the other side, this is heavily assumed that you have a lot of processing power, you can go up and down on the internet and get them. And you assume that always your server is on. Right? When you put your laptop on, you'll see the timing is showing some arbitrary value, but once it communicates with the server, you get back the timing. So this is dependent on your network, dependent on your CPU, and assumes that both up and down links are identical. And in that case, wireless networks will not give you up and down link identical links. They are different. So to see that, what we do is we have a very small energy and a very small computing power and a very small memory. And because of this, we are unable to put heavy algorithms into the system. We want a lightweight mechanism to extract the timing information. And we need, if you try to see the IoT and all, we are not looking at IoT in the home environment, but we are looking at a application where you have more number of sensors and so on. Okay, we have to look into that type of connectivity. So basically, all the algorithms or the methodologies what we try to use for IoT, we want some master clock should be there, and with the help of master clock, all the nodes have to be synchronized. So here the master clock is not something that you are getting it from outside. On one of the nodes you keep GPS and see that all the other nodes get synchronized to that. That's the main stream of it. So here, automatically when the master sends a signal, all the nodes will try to take their signal and adjust their clocks to the same value of the master. But it is not that easy, right? Because what happens when the master proper sends it, this node might be near to here and this node might be far. And if you try to synchronize everything to one scale, again there will be time scale difference, right? And the other one is, if this signal, even though I have drawn a straight line, it is not a straight line. We don't know the device, it is line of sight or non-line of sight. So the paths are not defined. So the timing extracting information will be random in nature. So in most of the cases, what we try to do is, the clock is always a linear clock. We don't have non-linear clocks, so you can see the time progresses as the time goes on. We don't see the watches which are running backward or running fast and slow. All these things will not be. Most of the clocks, if you try to see in nature, they are linear in nature. They move according to the time. They don't run away from these times, right? So we express it as a straight line equation, mx plus c. And we know that k is referred to as skew and b is an offset of the clock. And if you know exactly the skew and offset, you can know the timing of the information, right? But the skew and offset and all depends on lot of parameters, right? So when you see your watch, when you put a battery, new one, it runs properly. As the age goes on, it is decreasing the voltage. You will see that sometimes it is slowing down, right? Over a day, it will not run 24 hours. It might run 23 hours, 30 seconds or something like that. It slowly decreases the time as the voltages decreases. So these parameters, if you try to see, it is not that easy to say that it is mx plus c. You have another parameter called as plus error. And that error, if we can model it perfectly, then you know exactly what is the time, right? The rest of the parameters are constant. Offset is a constant value. It is not that varies every time, right? The skew is constant as long as your environmental parameters like voltage and other environmental conditions are same, right? If you increase the temperature in the room, the clock might run fast or it might run slow. Or if you change the pressure values and all, it might have some effect. Because what happens is in the IoT device and the sensor networks, we want these items to be as cheap as possible. The price should be as low as possible. We don't, suppose I say the bulb is there, you buy it for 1,000, nobody buys it. So I have to bring down the price of the bulb to something like 100 rupees or 200 so that everybody can buy. So when I am trying to drop the price going on, I have to look for a cheaper items to integrate into the bulb, right? So if I pick up a cheaper quartz for the clock purpose, that will lose time because they don't have the accuracy is what you buy it from 1,000 rupees bulb you have. So now I have to compensate that so that the customer will be very happy, right? Even though if I take a lower cost item, I should see that the circuit behaves as if it is the costly item or the stabilized items you are trying to put it. So that is prime important. And for that, you have to do a lot of exercise. It is not simply you buy and integrate and get it, right? So, but ideally the clock runs at a straight line equation, y is equal to mx plus c. And this is your skew and this is your offset. And estimating these two, in the absence of noise, it is perfectly easy. But in the presence of noise, it is not that easy. So this is what the clock is. So when you see 10 o'clock, it is 11, and 10 o'clock again you see it is. So if you take the real time 10 and 11, at the sensor node I, if you try to see if it is 10, it should be 11. And J, 10 and 11, if you draw it, you get a straight line, 45 degrees. because both are running at the same speed. Both the clocks, as 1 and 2, they are running in the same speed. When this is 10, this is 10. When this is 11, this is 11. And it's supposed to be, the real time is 10, this is showing 10, this is showing 10. And the real time is 11, this is showing 11, this is 1. So both are running at the same speed, hence you get a straight line with 45 degrees. Right? You can plot it out also. 10 is here and 10 is here, 11 is here, 11 is here. Right? So now, if we try to see the equation, the relative offset, relative means the difference of clock between these two is 0. And the relative skew is 1. They are running at the same speed. So now, if you try to look at these watches now, at the real time 10, this is showing 10 and this is showing 02. And at 11, this is showing at 11 and this watch is showing at 11.2, which means that there is an offset of 2 from the both the clocks, if you try to see. There is a change in the timing. So there is an offset of 2, 0.02, sorry, it's not 0.2, it is 0.02. So the offset is 0.2 and the skew are same because both are running at the same speed. If this is 10, that is 10.02. If it is 11, it is 11.02. So the speeds are same. So the skew is 1, and you can see that there is an offset over here, 0.02, but the speed is same, so it is 45 degrees. Right? So similarly, if you try to see here, the offset is delayed. Like this watch is showing 10, this watch is showing still 9.58, which means that it is lagging behind by 2 minutes, 2 seconds. Right? So they similarly here also, if you try to see, this is 11 and this is 10.7, the speed at which they are running is same, but only thing there is an offset of negative offset. It is not positive offset, it is negative. So you have minus, so you can see that the line has shifted here and still it is 45 degrees. So I think the terminology of skew and offset is clear. We are not changing those terminology. It will be continuing those terminology up to the end. Right? So now, what is troubling us? So when a packet has been generated, this is a machine which generates the packet. Right? Let us assume that there is an IoT machine which is trying to generate a packet. So it needs some time for pushing all the bits into the media. It is not that instantaneously there is a data rate at which you can transmit. So you have a pipe, you have a bucket of water. If you pour that, it will not go into it. Whatever is the capacity of the pipe only, you have to send it. So that's the meaning of the send time. You need some time to push all the water into the pipe. Right? So that we call it as send time. The time required to push all the bits into the pipe, we call it as k bits by r. R is the data rate, so that will give you the send time. So now you have another time called as access time. So I am ready with the data, but the channel is not available to me. I have to wait for my time slot to transmit it. So for example, let me go back and so red one has data, but it has to wait up to this point to transmit it. It cannot, just because it has data, it cannot push it over here. So that is what we call it as media access. You have a media, but you have to wait for your access time and then transmit it. So this is what the access time is. And then you have propagation time. The message has to move from here to here. The distance, if it is constant, the time period will be constant. Right? And since if it is line of sight, it is constant. If it is non-line of sight, it depends on the objects which are there, helping them the reflected signal to reach. So for example, I have a food truck over there, and the signal is striking there and coming to me from the base station. And the food truck has moved away, it has to go somewhere else struck and then come to me, because it is a non-line of sight. So this is not a constant one. In case if it is a wireless media, if it is a wired media, it is constant. Right? Wide dimension will not change, it is fixed. So if you connect two devices, the wire length is same. Okay? So if it is wireless, we are not sure the signal, which path it is trying to take, and hence there is some randomness in it. Otherwise, we can assume that if it is a straight line or something line of sight, it is constant. And then we have a receive time. So the data, when it is coming, you have to wait for all the packets, all the bits to be received, and then only you can do something. If it is half bits have come, you will not be able to do it. Until the last bit comes to you, you have to wait, and that is what receive time. The first bit and the last bit, whatever time you are taking to receive it. So now, if you try to look carefully, these are all random in nature. The first one, I have data, and the pipe is ready, so I can push it, but there is a limit on the bandwidth what is available. So right now I might have 1 MB bandwidth. Next second I might have only half MB bandwidth. Next time again I have 1.5 bandwidth, and so on. It depends on the channel. Like for example, if you try to see your Gmail and all, downloading or uploading, the bit rate will be varying. It is not a constant one what you get it. Right? At one instance you might get 1 MB. At the second instance it might be only 1 kilobit per second, and later on it might drop to 20 bytes, 40 bytes also. That depends on the load of the network at that instant of time. How much bandwidth you got it to transmit it. Access point, if it is time division, I know my slot when it comes. If it is not TDMA, if it is Aloha or CDMA or CSMA and all, I am not sure when because it is a carrier sense. Whenever the carrier is free, I can only transmit. Right? So the access time is random. Propagation time, as I told you, the wireless networks, if it is short distance, you can take it as constant, but if it is a multi-hop network, then it will be difficult. Receive time also depends on the processor load at the receiver. It might be doing multiple operations, then the receiving might be slow. If it is free, it can receive everything. Like for example, I am at my desk and the mail has come. I can take it. If I am doing some exam paper correction or something, I'll ask, wait, let me finish up this and take it. Okay? So now if you try to look carefully, all these parameters are random in nature. They are not constant. And this randomness will try to create problems for me in estimating the time. Right? So I have to model this randomness such a way that I can find out my offset. Okay? So there are different algorithms which are available. It is not that there are only 1 or 2 methods and all. They are, like you can see in the literature, you will have some hundreds and 200s type of synchronization algorithms, because most of the people, if you try to see, they used it for different applications. And all applications doesn't need the same accuracies. So they are dependent on different methodology. So they are popularly, if you try to see the initial stages and all, there are 3 good algorithms here. You can call it as a benchmark algorithms, over which people are trying to compare their algorithms and say which is good, which is bad and all. So if you try to look like that, there is a reference broadcast synchronization algorithm, and which is very good algorithm. In fact, during that time it has a lot of popularity, but now people are not going into that because it consumes a lot of energy for synchronizing the network. And there is time protocol synchronization and FTSP, and we also have developed some algorithms in that direction. So if you carefully try to see this algorithm, RBS, what they primarily try to do is the source means the beacon, the node which has GPS and which can help the others to synchronize, right? So this is the master node. For example, I have shown you in the beginning, there is a master clock. So this is what is the source, and these are the receivers. So when we go back to the source tries to transmit the information. This is my clock, and all have to be synchronized to that. So now you have 2 types of synchronization over here. When the source says that this is the synchronization, it means that the source can get a global clock, or it can be a local clock also. So some applications you need global clock because you are pushing this data into the internet. Some locally you are trying to monitor it, global clock is immaterial to you, local clock is sufficient for you, because you are not pushing into internet and doing some applications and all. So like I have a monitoring station to monitor the attendance. So this is sufficiently fair enough for me to get the timing and put it. And even if it is 5 minutes or 4 minutes, this way or that way, it will still survive because I am taking class attendance from 10 to 11. It need not be exactly at 10 or exactly at 10:05 or 10:10 or, okay. So in between 10 to 11, I can take a class. So I need not have to precisely go over there and come back. I can use a local clock over here. So this is what we mean it. So the source can have either a global clock or local clock, and the application will tell you what type of clock you need it. And then the master will try to send the information, my clock time is this. So all of you try to adjust it, right? So when it says it, the receivers, what they try to do is, the receivers share the information. I have received at this time. The another receiver says, I have received at this time. The another receiver will say, I have received at this time. So now you know the offset between you two. So the receiver to receiver offsets will be known to each other, because I have received at 10.02 and he will say that I have received at 10.03. So the offset between we both is 0.101, right? So each one can calculate their offsets. So if I want to talk to him, I will adjust the clock such a way that I can talk to him real time. Okay, 0.01, I'll adjust the transmission time and say I am transmitting at 03 to him. So I'll adjust 0.02 to him and say that this is my time, right? So now we are trying to locally do that, and hence what they claim is, if you try to go back to over here, since you are sending all the people at the same time, this is common for all. And the access time is also common for all. You have accessed the network and transmitted it. So these two has no meaning for me, and hence mine is more accurate. That's the claim they try to do. I hope it is clear. Because he is using the master clock to inform everyone, right? So the send time is common for all the people. The access time is common for all the people. So these two have no effect. The only time is these two, and that's what the algorithm is. And they inform this one is that, and they cancel out. The common two values, they'll get cancelled, but the rest two will be there. And hence they say that my algorithm is more accurate than others, because two of the parameters they have reduced it out of 4. I hope it is good over there, right? So coming to the next one, TPSN. And this is almost like your NTP protocol, right? The master clock, I got it. I'll send back the information. So the NTP mostly work on that concept only. There is a master server thing. You request it, they'll send the information, you request it and adjust it to your clock and do it. So now, if you try to look into that model, if the uplink and downlink are identical, this gives you a good result. And if they are not identical, then the problem starts, right? If the uplink and downlink are same, then you can divide by 2, because they use divide by 2, average of it, and then try to approximate it. And if they are identical, then you have the best estimate. If they are not identical, the estimate is wrong, right? So every node will have to do up and down. And hence you see that the broadcasting energy is more in the case of TPSN. And here also it is more, because you have to talk to every node in the network. Suppose there are 1,000, all the 1,000 you have to broadcast. Again, the other one will again transport to 1,000 nodes, and so on. And coming to FTSP, it is sender-receiver synchronization. It is almost similar to our type of communication. You can see the number of lines have been reduced, which means that it saves a lot of energy in synchronizing among themselves. You need not have to exchange 4 lines over here, 3 lines over here. Here it's only 2 lines. But the problem is, we assume that the packet reaches the destination. If the packet doesn't reach here, we are not sure whether it has gone or not, right? So the only assumption is we are trying to send the packet, so you have to do it. So the change what we have made in our algorithm is, we define that if you don't receive a packet within a bounded time, the packet is lost. We don't need to worry about it, right? So we fixed up the bounds on the time, and we are trying to minimize the error within the bounds. And slowly you reduce the bounds to a point where you can say that this is the point at which your time is being synchronized. So since we are using unidirectional, the energy is minimum because bidirectional consumes more energy. Up and down you have to do. You are doing only half of it, so you get a unidirectional one. And we have a very good paper in that ECTI transactions of electrical engineering and electronics and communication. So we gave you the complete mathematical treatment over there, how to analyze it, minimize it, and get back the values and all. And broadly, these are some of the algorithms which popularly people try to modify it and try to get a very good result on it. And you have to see that the error in estimating should be as small as possible within microseconds or nanoseconds. Because most of the devices, they prefer nanoseconds because in VLSI or the cross connects and all should be nanoseconds or less than that. So in that cases also the algorithms still try to help you out. So this is a small comparison between the FTSP and our algorithm. So you can see that these people try to use linear regression method to find out, estimate their clocks. And the problem with this is they need larger memory because once you want to use linear regression, you need a data set for it. So you have to use the data set so you need a memory to store all the values and then find a linear regression for that. Okay? So the point estimation uses one single number, the best estimator for the error offset corresponding to the n data sets received. So mostly these people have done on single point estimate. Point estimate they try to do, and they find out the point, how much is offset, how much is skew, and so on. Right? And we have a different mechanism where we update the values. We don't store the values. Once we get a value, we update it to the next level, and we forget about the past. So the memory is not a demanding issue on IoTs. So whereas the previous one, there is a small slight catch over there. They need a larger memory. And the device, if you try to program it, you don't have space for the memory to store all those values. And hence we say that our thing is like updating the values. So if the old value is good, the new value will be discarded. If the new value is good, the old value will be discarded. Okay, so the updates the error interval after each message packet, and interval estimation uses a better estimate than a point estimate. Interval estimate is much better than a point estimate. That's what our claim is. And hence it has been accepted, and we got a very good feedback also on that. Any questions? So now we have used a 100 node network to find out how exactly the energy is consumed and all. And you can see that our algorithm is almost similar to FTSP. And whereas these two RBS and TPS are consuming more energy than the required energy. And this is in, you can see 10 to the power 5 nanojoules. And this is as the packets increases. So if you need 10 packets to synchronize, you can see that the energy is compared to the other two is very small. And the maximum number of hops what we got is 19 hops is the network. And you can also try to increase and decrease the number of simulations and all. Right? So this, oh sorry. Okay. Okay, the localization part is missing over here. Continue from where we have left in the morning because I am left only with few slides before we actually move on to the demos. So the localization part, if you try to see, we should know exactly where the nodes are lying because we have many applications which tells us about the routing protocol. Suppose I want data from some part of the campus. I should know the locations of the sensor so that I can ask, okay, room number 302, report me the attendance status or something. So the localization helps us in finding the exact location of the target as well as the source. Source localization is there, target localization. So for example, if you want the target localization, you can think something like a ball which is moving on the track of a cricket field, you can exactly locate the ball, how it is moving, and all the directions can notice it. Similarly, source localization also you can do it for finding out exactly where the sensors are. Okay, so localization can be viewed as source or target localization. It's not only one we are trying to do, two also you can do it. So here we have the basic requirement, something like we have to find out the location of the node by not going near to the node, because some places which you are not unable to go there, like suppose there is a volcano erupt and you want to monitor the situation continuously, you will not go near to the volcano. You drop the sensors around the volcano mountain and then try to monitor how the lava is coming up, what is the temperature, how the lava is moving, all these things you want to monitor it. So in such cases, we should know exactly the locations of the sensor so that we can track down the trajectory of the events what is going on. So it is not possible to find out manually. Manually we will not go and find the locations, and the location information is required for some applications. It is not that all the things need the location information, but some application demands, like for example, I want to monitor the line movement, that is target. So when it is moving it, I should be able to localize the target and see how the target is going on. Yeah, so that is what we call it as target localization. So when we are trying to do that, high precision is required, otherwise we will be assuming that line is coming in this part, but it is moving 100 meters away. So the precision of localization is prime important in case of tracking the objects very accurately. For example, you might be seeing on the TV the ball is coming at the speed of 100 kilometer per hour or 120 kilometer per hour. So they are able to track it so accurately so that they know how the target is moving, at what speed it is moving, at what angle it is moving. Everything can be recorded. So this is important, and again, as I told you in the time synchronization, we are not able to put the GPS on top of it and track it, because it needs a lot of energy, and these nodes don't have so much energy. So we have to look from the cost and energy consumption also, and we have to design our circuits based on that. So we have two types or classifications of algorithms. One is range-based, other is range-free. One is you try to find out the position. For example, I am standing here. I can easily find out my location, saying that if I know these four corners, I can easily find out my location. I'll find out the distance from here, distance from there, and 4 points where they meet. That is my location. This is what we call it as range-based. I have to send some signal, I'll get back the response. Again, I'll send some signal, I'll get back the response. Again, I'll send signal, I'll get the response. So all these responses where they meet is my location. And there are some algorithms which don't need these ranges. They can find out where exactly it is. For example, if I say that where is Sai Prakash, you can clearly say that he is in the room number ECE conference hall, because I am well within the defined area. Okay, so the accuracy will not be there in case of range-free, but in case of range-based, you have the more accurate result, right? But if you try to see, when you are going towards the accuracy, you have to spend more energy and cost and everything. If you increase the cost and hardware and everything, then you get more precise value. If you are not spending much of your work, then you can say that, okay, he is there in the conference room, right? So that is the difference between these two. One is cost-effective solution, one is like accuracy you have compromised for cost. Okay, so this only tells you, like some applications, like you just want to know where Sai Prakash is, range-free is sufficient for you, right? Because in the department you can say that I am in this room, it is sufficient, right? But they want exactly what I am doing, how I am moving in the department and all, then I have to go for range-based. I will not be able to do it with range-free. Okay, so that's what is written. It is cost-effective, much cost is not required for this, but here you have to put some cost on it to get back to the values. So now, what are the methods to send a signal and get back the information? So we have three popular methods. One is RSSI, one is time of arrival, time difference of arrival. And both are time of arrivals only there is a word called difference. So for example, I am trying to use some electromagnetic signal to transmit and get back the, like radar. So I send the signal, I'll get back the response, so I know the distance between myself and that corner point. So now let us refer the corner points as beacons. Beacons are nothing but the elements which know their location. Somehow they know the location, whether it is GPS or whatever it is. They are beacons which know their location, and from them I am trying to find out my location. So for example, if you try to see, most of the people, when you order something, they ask for a landmark. Right? They don't bother for your address. You just say some landmarks. So you will say that, okay, I am opposite to the post office, or I am opposite to the LCT office, or I am opposite to NIT, or something like that landmark item you will say, and then they find out they use range-free algorithm. Because they need not have to spend much energy and all, come there and then call you and you will say, I am standing out and something. Right? So that's what is range-free. You are not estimating, you are calculating your distances. You are saying that, okay, you come there, call me, I'll come out. Right? Whereas here, we are not doing that. We are sending a signal and getting a response. Based on that, I am trying to calculate. So now, the interesting part is, when we are doing that, we have one beacon, and I want to find out the range. So this is my target, or the sensor node, or IoT, and this is the beacon. So what I do is I'll send a signal and I get back the response. I know that it is 5 kilometers away or 2 kilometers away. And I will not be able to estimate my location because it can lie on any of these 2 kilometer range. Right? I can be anywhere on the 2 kilometer range. The beacon is here and sensor is here, so I assume that beacon is anywhere on the 2. Right? So with one beacon, we will not be able to estimate the distance. So now, if I move on to second beacon, so I will have another point which I will be trying to move around. So now I have an option that I might be either in this point or in this point. With two circles, if you try to draw the ring, there will be two intersections. So there is a possibility that I might be on this side or here. So the estimating your distance is not that easy with one beacon or two beacons, and a minimum of 3 beacons are required for doing that. So now I know that I will be lying on this area only. Right? So now I know that I am here, so that this beacon I can hear it, this beacon I can hear it, this beacon I hear. So if I know the distances properly, then it is something like exactly you can cut at one point. If I know the distances accurately, you can see that the intersection of the 3 cycles will give me the location. So if it is 2, you have 2 points and you will not be able to estimate. Right? So a minimum of 3 is required to find exactly where you are. But again, as I told you, your measurements should be accurate. And if it is not accurate, then you will have a region over here, not a point. Right? So whenever I transmit and get a signal, the measurements are estimations only. They are not exact. Because I am not putting a tape and measuring, I am sending a signal and getting back. So they are, we call it as measurements, and those are not exact values, they are approximate values. So that gives me a small variation over here. And that itself will tell you how good your algorithm is. And if this is 1 meter, you can say I can predict with 1 meter accuracy. If it is 10 meters, you have to say that I am predicting your location by 10 meters accuracy. So always you might be seeing that the mobile lost and mobile somewhere they traced it and all. They say that 100 meters within the range, there is your mobile is seen over there. They will not tell exactly at, okay, this apartment, room number so and so, they will not tell you. In this locality only your mobile is there. Because they are using some 3 base stations, because they don't have so many base stations that they can send signals and all. So there will be 1 or 2 base stations or 3 base stations. So from that they can only estimate the location in that area. Right? So now this transmitting and getting back the signals is what we looked at as received signal strength indicator. So if you try to see the signal received by your mobile, there will be 1 line, 2 lines, 3 lines, 4 lines, which tells you how far you are from the mobile station. So based on that signal strength, the algorithm tries to work. The second one is time of arrival. So I sent a signal, I got back the response, so the time difference or the time of getting the signal itself will tell you how much distance far it is, because you know the signal, electromagnetic signal travels at 2 into 10 to the power of 8. So you can calculate the distance. The time you know, the velocity you know, so the distance you can calculate. Right? So now we have one more over here, angle of arrival. Right? That is also a part of range base only. And mostly you need some extra hardware to find the angle, transmit and get back the angle and so on. Right? And then what is time difference of arrival? See, time of arrival we know, we transmitted and got back the signal, we know time of arrival. Time difference of arrival is something very interesting, where because what happens is when you transmit a signal, the signal might hit the target or it might be coming from the neighborhood of the target. That is one reason. The second is, if you try to see, the velocity at which the signal is traveling is 2 into 10 to the power of 8 meters per second, which means that your measurement value will be microseconds. And measuring that microseconds will be very difficult. Right? And that will lead to errors. So what we try to do is we send 2 different signals. One is electromagnetic, the second one is sound signal. So we know that sound is traveling at 330 meters per second, and the electromagnetic signal is traveling at 2 into 10 to the power of 8. So the difference of that, we use it for calculating them. And this gives you more accurate results than time of arrival. Right? Because both have started at the same time, but both will reach differently, and again getting back will be different. And please remember that this is not a bidirectional one. The beacons will send the signal, and I estimate the values. Right? I am supposed to find my location and then tell others this is my location. Okay? And once I get it, and once I get this error, whatever is the measurement values I got it, I have to compute this point, xy point, x0, y0 point, once I get these signals from the beacons. And now how to estimate x0, y0. So we know that there is a Euclidean distance equation which tells you between x0 and x1, x0 and x2, x0 and x3. And just if you get your simultaneous equations and solve for E1, E2, solve this set of simultaneous equations, you get back your values x0, y0. Right? When we use that, automatically you get back your values x0, y0. And now you have an error because you have not got the exact value. You will get some error. So you do it iteratively until you get your signal error difference is 0. So this E0 should go to 0. Until then, you go on rotating the iteratively, you try to modify, and then get back to EI0, which tells you exactly where you are. So what I'm doing, as I get it, there is an error point, so I move this way and find the error. I'll move this way and find the error, back and find the error. Which one is minimum, I'll try to use it. Right? That's what we are trying to do in that case. Now coming to the other set of algorithms, range-free localization. So it only gives you the centroid of a given beacon area. right? If I can hear 3, I am there in center of, it is a triangle now. So in the triangle, I am there somewhere here. The other half, I am not there. So, and you go on decreasing your radius if you have more and more beacons. If the beacons are less, the error will be more. And drawing this centroid is also much easier. Now there is a formula for centroid. 5 faces if you have 5-face polygon, we call it as. So you can use the centroid of a polygon and find the location. If it is a triangle, centroid of a triangle, you can find out. Square, centroid of a square, you can find out, and so on. There is another method which we popularly use is graphical method. So what we try to do is, you try to take an area and you know it is there. Your sensor is there within the area. So now I move this one, displace it and see whether I am there in the area or not. Still, if I am in the area, I will try to display it and try to find the area. If I am still there, I will try to find it out. And now what I am trying to do is, I am reducing my error area. And I go on repeating it and find out whether I am there or not. If I am not there in this direction, I have to move this direction or this direction, so that I know my location and go on. So this is what we call it bounded boxes type of algorithms, right? And generally we do this type of things for larger areas. When we have very large area, we want to converge very fast. We move the box very fast from one direction. And if you are missing it, we move on to the other direction and below, and we will get to a location. And this is very easy in simulations, because in the simulations we write for x and y. So keep x constant, move y, and then keep y constant, then move x, and you get to the location, right? But physically, if you want to implement and see, it takes longer time, right? It's in a loop you are trying to do, and moving it one direction, it is simpler. And again, in a loop, other direction is also simpler. So mathematically, it is much simpler than actually going to the location and finding it out, because the equipment will not move like that in the real scenario. And the only thing is, if you want to do that, you need some drone or something which flies in one direction, one side, and next other direction, we can try it out. So this is about the general idea of how the localization is being done. And why we want to do this type of algorithms or location finding and all is important to us. Suppose people are saying that I have seen a tiger in that location. So now we can estimate the location where it is and try to monitor only that area. We need not have to monitor the complete area. So that is one precise thing. Like for example, as I told you in the first class, there is a fire accident and they have to report to the office. So suppose he has gone out of town and there is a fire. The office has to find out exactly where it is. It is not that somebody will call and then they will move and all. So the localization will help them to find exactly where the target is, right? Because the data which is coming on has some type of, what you call it is, there is a deviation in the data, okay? So which means that data is not as it is what you are getting it. You are trying to find some type of, what is the name? We have done it? Anomaly detection method. So we find out anomalies in the given data set, and as and when we find the anomaly, we try to scan which area is generating that, and precisely we'll go to the location. That is one thing. So second thing is, when I want to move data on the network, I use geographical location routing algorithm to find out the location and go to that target, and only that target will be visualized. Like for example, there are 100 classrooms in the campus. I want exactly to find out the classroom 201 is active or not. I will not go through all the classrooms and see which room 201 and all. I only ask 201, report what is the activity over there, right? So geographically, the sensor network or the IoT network should locate that one and go exactly to that and report what is happening in the classroom. And that is what precisely nowadays in most of the administrative block and all they try to do. The director need not have to go anywhere. He'll just ask room number 201 and he'll see what is going on over there. Right? And now, since biometric has came, people are smart enough. So recently there was a query saying that the class has only 26, but the attendance is reporting 38. Right? I think it's a well-known fact in the campus. So he located that. He is watching one room, and he is showing that there are only 36 students, and the attendance is showing 48. Right? And now it has become another scenario, like teachers are supposed to monitor how many students are active in the class. So we are doing double duty, saying that, okay, so many students have come, and we take manual attendance, and we'll compare it. Whoever has done the fraud, we are trying to catch them. Right? So there are different ways of finding the location and how exactly we have to get into that and all. And there was one case also, like we have the biometric at the gate also. After the college officer who is going out and coming out, they have to be monitored. So they found one wax finger strip also over there. Recently it happened. Okay? So, and now it's not difficult to catch it. It is very simple because we know who has entered the data at that time. So we sent a note saying that you come and report. So later on the boy has agreed that he has done it, but it's not difficult. Like, people should not assume that it is very difficult to catch and all. It is very simple to catch it because the record shows that you have recorded it. And the camera over there has shown that you have been passing through. Right? So the things are happening, but please remember that the localization helps us in saving a lot of energy on the network. You need not have to ask all the network to be active. You can directly go and wake up the IoT and then find out the instance. Okay, for searching the rooms, I need not have to put on all the 300 cameras on the campus and start searching. I can directly go to the room number, wake up that light or camera and all, and I can see who is doing it. So localization helps in energy and the cost effectiveness and the, what we say, the effectiveness of the network also improves. So with this, I am stopping on this localization and time synchronization. I have given you a brief idea of why we have to do synchronization, what are the methods available, why we have to do localization, what are the methods available. So we go to a range-based, you get more accurate. If you go for a range-free, less accuracy, the cost is less, implementation is less. Range-based is costly, implementation is hard, but you get more accurate. Right? And now people are trying to do a lot of research work on this, and they are trying to see with Wi-Fi can we localize the people in the campus or not. Right? In the department, I don't get GPS into this room, so I use these access points to find exactly where you are, because once you move around, your mobile is connected to the access point. I can know easily what are the signal strengths at 3 Wi-Fis, and I can locate your location. Right? So for that, if you want to have a knowledge of it, there is a app on the mobile phone which you can activate it, and you can find the RSSI of your signal from the Wi-Fi. And it also tells you how many Wi-Fis are in your range, what are their RSSI. So based on that, you can easily find it out. Okay? So with this, I'll stop over here, and we'll move on to the demo parts. If you have any questions, I can answer them before we move on. Okay, then, thank you. We'll start with